I'm Ankit Kangwan, and on behalf of my co-authors Akash Jain and Mauro Conti, I will present our work on the feasibility of profiling electric vehicles through charging data. This talk is divided into 4 parts. One is the introduction, EV profiling, results, and conclusion. So electric vehicles represent green substitute for the traditional fuel-based vehicles, and they are becoming increasingly popular day by day. These electric vehicles require recharging. We can recharge them at home, and the public charging points are also becoming very common. And for natural reasons, when we are away from the home, we only have the option to recharge at some public points, say, for example, in the office or some roadside charging point. The overall EV charging process can be divided into 2 parts. One is the resource negotiation phase, where we securely exchange our private information, for example, login credentials and credit card information, etc. And the second part of this charging process is the actual charging phase, where we transfer the electrical signals to recharge the EV. This phase is usually unprotected, which means that it can be exploited as a side channel to profile the batteries or even the electric vehicles itself, which raises the question of the privacy of a EV user when he drives from one place to another and uses different charging points during the journey. Electric vehicle batteries are mostly lithium-ion batteries, and such batteries, they have a distinct charging process, which means they follow a fixed profile. So on your screen, what you see is a constant current, constant voltage charge profile. In this constant current phase, the voltage is varied, while in the constant voltage phase, the current is varied based on the state of the charge of the battery. And this current in the constant voltage phase is called the tail of the charging profile. Recent works, such as the 9th, 10th, and 11th work, have used this data from the charging phase to profile the batteries of the electrical vehicle under certain assumptions. The work number 10 and 11 are called EV Scout, and they represent the state of the art of the EV profiling approaches. In this work, first thing we propose is an improved EV profiling approach that outperforms the state of the art. And next, we evaluate the feasibility of profiling and individually identifying EVs at the scale. Similar to the state-of-the-art works, we assume that the attacker has gained access to the public charging points and have also modified the charging port to get charging data about an electrical vehicle. After gathering this data and storing it into its system, the attacker filters noise from the time series data, also identifies tail, and extract features to get models for binary and multi-label classification for the profile user EVs. In the work, we have used ACM datasec. In particular, this dataset consists of charging data for about 885 unique EVs from 2 charging locations. In our work, we use 3 parameters, which are user ID, pilot signal, and a charging current signal. After an initial filtering, we got over 25,000 samples from over 500 electronic vehicles. And this dataset is what we call our complete dataset. And from this complete dataset, we created smaller dataset called small, medium, and large dataset that are comparable to the dataset considered in this state-of-the-art works. So we begin with the binary classification, in particular one versus all approach used in the EV Scout 1 and 2. Here what we see is our approach not only outperforms the state-of-the-art, that is EV Scout, but it also gives very consistent and stable performance in terms of identifying the vehicles. Next, we move towards multi-class classification, in particular because in multi-class classification, a given sample can only belong to one and only one class, while in the case of one versus all approach, every unknown sample is passed through n different models, and a certain confidence score is calculated upon the unseen sample. So in this current classification scheme, we see that the performance of different classifiers it decreases with the increase in the size of the dataset. So what we do next is we try to understand the effect of number of samples per EV and the number of EVs in the dataset. What you see here is with the increase in the number of samples per EV, the performance of our approach increases. This is true for all the 4 dataset that we considered here. But what we also see here, with the increase in the number of vehicles in the dataset, the performance of the profiling approach decreases. Next, we also evaluate our approach with subsample datasets with synthetic distribution. So we created synthetic normal distribution and synthetic uniform distribution from the complete dataset that we had. And we find that in any of these cases, the performance of EV profiling does not exceed 50-55%, which is roughly equivalent to flipping a coin when guessing. So to conclude, in this work, we propose an improved EV profiling approach that outperforms the state-of-the-art work, but also gives a very stable and consistent performance. However, all these works, including ours, is only enabled because of the EV identifiers present in the public dataset. So in a real-world scenario, associating a charging sample to a given vehicle is very difficult in the practice. Moreover, our results also show that profiling and individually identifying EVs at scale appears to be very difficult in practice, which is what generally claimed into the state-of-the-art work. So our work serves as a means to define or to show that this profiling is really difficult in practice, and the EV adopters or the future owner of the EV vehicle should not really worry about it as with the present approaches. In the future, we will investigate other avenues for practical EV profiling, and if such avenues exist, we will work towards finding such possibilities. With that, I thank you all, and I'll be happy to take any questions you might have.